Hey people, what's good? Matplotlib. Hope everybody's doing great. Welcome back for another video. And if you're new to the channel, welcome. I yap a lot about signals intelligence, electronic warfare, and some other specialist breakout content. So hopefully you'll stick around for the rest of the video. This is part 2 of the ongoing series on RTL-Power. In part 1, which is linked down below in the video description, I went over a deep dive into RTL-Power, the various ELINT and COMINT use cases for it, how you to understand the command line, and then just ran some simple scripts. That's the collection phase of the intelligence cycle. Today we're going to focus on the processing and exploitation phase of the intelligence cycle by actually getting the output, that CSV or quote-unquote CSV data that RTL-Power outputs, and then we're going to help you process it. I'm going to help you visualize it and do a couple other things with some Python utilities. Now, all you're going to need for this is a RTL-SDR. Doesn't matter if it's a V3 or V4 or an old SDR stick or anything else that has a SOAP SDR drivers compatible with RTL-Power. And I'm going to be demoing off of a Raspberry Pi. It doesn't really matter what you use. I believe RTL-Power is supported on all 3 of the major platforms. There's also another video linked in the video description down below on how to install DragonOS, which comes with RTL-Power, RTL-SDR, all the various drivers, and hundreds of other signal intelligence specific utilities for you to use. So I'm going to go cut over to me on the computer and we'll go ahead and get started. And also, before we do that, the code that we'll be using is in Pastebin and is also linked down below, so you can take it. I know that not everybody knows how to write Python, and honestly, it'll be a lot harder for me to teach you how to do that. So hopefully this video will serve as a good aid for you to follow along, even if you don't have any Python skills whatsoever. Let's get started. Here we are, and before we get started, in the last video, which is also linked down below, just like I mentioned in the intro, I talked about using VS Code as your integrated development environment to connect over Secure Shell or SSH into your Raspberry Pi or other device that's running DragonOS, and of course you could SSH on a ton of things. Pretty simple, just Google up Visual Studio or Visual Studio Code, and then come over here and download. You see it's supported on pretty much every single system, every single architecture, except notably no by32, so no 32-bit systems on Windows. So if you're using something ancient like Vista or XP, well, you're kind of shit out of luck and you'll have to go with something else. And then the next thing that you'll need is the remote-SSH extension. That previous link and this link are also in the video description down below. And this is the utility, the extension inside of VS Code that allows you to connect over SSH. And simply what you would do, I'm already connected into the box before we get started here. So you would just click on the little icon, these kind of 2 different caret icons, connect the host, and then you would go ahead and type in Ubuntu if you're using DragonOS at whatever your IP address is, or a host name if you gave your Raspberry Pi a host name on your internal network, and it would save that for later so you could keep reconnecting to it, and then open up the /home/Ubuntu or /Ubuntu/home, whichever way that is, to open up this folder. And this is essentially the desktop that you would see if you plugged in your Raspberry Pi to an external screen. Minus a lot of these other folders that are that begin with a dot. Those would be hidden on your desktop inside of like the DragonOS UI. But to get started here, and if all you care is about the code, it's also in a Pastebin link down below. I think it's the first link in useful resources that I put underneath the video. But this script encapsulates the processing of the actual SSV, space separated value format, or CSV as RTL calls it, but it's not CSV because it doesn't have any header data. So this processes the data, and then we're going to save it to a data frame, and a data frame is just a type of logical container for data. It's used a lot in big data analytics using the pandas library, which is also linked down below if you want to read some more. Save it as JSON data, which you don't need to do unless you're going to read this out into something else or process the JSON data to put in a data lake. Now, I wouldn't actually use JSON for that, and if you're curious to know more, I could explain it in the comments, or I could do another video. This super deep dive technical content doesn't typically do as well as my other stuff showing off the kit, but this is equally as important. In fact, this is more important than the kit, honestly. This is actually doing something with the data. If you're just using your SDR to collect data and not doing anything with it, then I don't really understand the point. Calculating out some noise floor, building a scatter plot. So this is everything about the scatter plot. And I left, more comments than I typically would writing code in here. And this code's very monolithic. It just runs one after another. So there's no input, because I know that not everybody has the same skill set, but hopefully this does inspire you to go get the skill set. Over here is how we build the heat map. Again, using Matplotlib, if I didn't mention that before, link down below, noticing a trend here. So this is just a different view on top of the scatter plot. The scatter plot, we'll take a look at it a bit later. We'll obviously be able to see a couple more details, and then the heat map just kind of normalizes everything. This is DuckDB, so this is how I execute SQL queries working with local files. SQL is structured query language. It's essentially the language of databases. So I don't know, I've never been to college, but if you've been to college and you took a comp sci class, I could almost guarantee you that your smelly ass professor probably showed you MariaDB or PostgreSQL or MySQL or, Microsoft SQL Server, something like that. That's what this is for. DuckDB is a in-memory vectorized analytical database. So essentially an in-memory data warehouse, which allows you to interact with your data column-wise instead of row-wise. So a traditional database, also known as an OLTP, a online transactional platform or online transactional processing database, does everything row-wise. So it reads row by row by row. And a database table is, just think of an Excel, or think of a real CSV. If you ever opened up Excel and you put data into a table for like your budget or whatever, if you're buying a new car, that's essentially a table. Fields are columns, rows are just, actual rows. So SQL allows you to interact with these rows using this. And then we also plug in a extra argument inside of here, giving it the noise floor. So essentially what this does is, hey, give me everything where the noise floor is, where the value, the dBm, right, that receive signal strength indicator is above my noise floor. And you could also tweak that to your own needs, and give me the maximum, the max dBm per frequency, because depending on how long your sweep is, you could end up sweeping the same frequency bin multiple times. Remember, frequency bin is just a subsection of frequency. It dumps it back out as a data frame, prints the top 10 results. This is a little redundant because limit 10, head 10 is pretty much the same thing. You could also take the limit out if you wanted to, and I'll probably do it when I work it through. And then this last part creates you a animated flowchart. You could save this as MP4, but I'm saving this as a GIF. And again, this is important if you're, well, not to say important, but this could be useful for you if you're taking really long samples with RTL-power. Let's say you left this running for like 15 minutes over across like a 20 megahertz of spectrum, right? So all of mirrors, all of GMRS, all of FRS, all of public safety bands, 700 to 800. You could crunch through that thing pretty fast, so you'll get multiple samples over a time period. So you could see any measurements, and that's good for more like Mark 1 eyeball analysis. But anyway, that's all I really wanted to explain with the code. If you write Python, then you probably could already tell that this is pretty terrible. And if you don't, hopefully, again, you'll just pick it up a little bit, but you could just, the only thing you need to change is this, the RTL-power output file name. Whatever you save your file name as, just change this part right here, and then everything else will run as long as you're in the same directory. And speaking of, let's get started with that. So when you get into DragonOS, and I'm just going to assume you are, just click anywhere on the top files, and this doesn't really matter, this is a wisdom file. And this little icon right over here, new folder with a plus and a folder icon, go ahead and do new folder, and let's just call it RTL_power_ part 2. And then what you're going to do is right click this, and you're going to open integrated terminal. So it's going to pop a terminal open under here inside of VS Code. Again, this is called an integrated development environment. So we can do multiple things, interact with extensions, SSH, debugging. We could play with Jupyter notebooks, run Docker containers, stuff like that. Now from in here, right click the folder again, and then click new file, and then give it a name for your Python script. So RTL-power_script.py to make it a Python file. Nice and simple, nothing too crazy. And then I'll just copy and paste this over to here. But before we do that, let's install some software dependencies that you are going to need. And once again, they're down below, so you can just copy and paste them and run it. So from your terminal, the first thing you're going to want to do is a sudo. That escalates your privileges because you need that to install things. APT, that's shorthand for aptitude. That's the package manager for anything in the Debian Ubuntu family like DragonOS. Install -y command will just automatically install it instead of prompting you to say yes. and then you're going to do Python 3 dash virtualenv, and that installs a library called Virtualenv, which isn't to be confused with like VirtualBox or virtual machine. A virtual environment allows you to create essentially repositories of software dependencies. Different Python scripts, different modules, different tools all have their own dependencies. You've probably seen that with like RTL-power if you compiled it from source and whatnot, which is why, again, use DragonOS just because you don't have to mess with any of that. So there might be different scripts and different tools that have different dependencies because software changes, right? That's pretty obscure for us as just regular civilians if you don't work in IT, where you're using, I don't know, TurboTax or QuickBooks, or you're using your bank app. They probably go through multiple software versions, adding new features and such, but you can't really tell because you just log in, you get whatever the latest is. However, there's stuff that's pinned, it's called, to certain versions where it's like, hey, this must be version 1.5 instead of 1.7. So a virtual environment allows you to segregate these different things for the different scripts into their own little directory. So you just hit enter, default password's Dragon if you haven't changed that. And then I already have it installed, so no big deal. And then the next thing we're going to want to do is actually start up the virtual environment. So Virtualenv, rate it again, -p, that tells you the Python version. We're going to go with Python 3-12 because as of July 2025, that's the latest Python version that's already installed here. You could probably go higher, but no real need. And then space and put a period, which means this current working directory that we're in, this folder that we're in essentially. And then it'll set that up, and this little pop-up, hey, we see a new environment, just hit yes, because that'll register the actual libraries. And you can see the script that I had open, is now, there's a bunch of red squiggly lines because we actually don't have those. So that's another great thing for the IDE. You get syntax highlighting, you get some easy debugging, and this is like, hey, this isn't installed in your virtual environment. So now we actually need to update our virtual environment. So we're going to type in source or activate it /bin, bin, short for binary, /activate. And that'll actually put us into our virtual environment. And then the next thing we're going to do is install the software dependencies we need up here. So pip3 install pandas space matplotlib space DuckDB. Go ahead, run that. And then it'll just go ahead and collect all of the packages that are required, and it'll go ahead and install it for you. You can see I have a lot of them cached locally because I've done this a couple times, just making sure that everything's good to go. And then you could just ignore it from here. To exit your virtual environment, you would just type in deactivate. This virtual environment is different from this one. This is just for type hinting. This one is for your local. So now anything that we're running with Python is only using the dependencies from this virtual environment we just created. So again, like I mentioned in the intro, you don't have to follow this word for word, right? Because obviously all our scans are going to be different, so it doesn't really matter unless like you live down the block from me, which would be weird. I would probably know you. Anyway, to make sure that it's plugged in, if you're using an RTL-SDR v4, there's a little red light next to the SMA port. But if you're using an SDR stick or v3 or something else that is an RTL-SDR, you'll type in lsusb. That's just list USBs. And then as long as you see this RTL2838 DVDB-T, that means you're good to go. And then we'll go ahead and run our RTL command. And I'm just hitting the up button on my keyboard to go through this. So RTL-power -F, remember, we give it a lower frequency and upper frequency, and then the bandwidth. So I'm starting at 150 megahertz, ending at 170 megahertz. 12.5 kilohertz channel bandwidth, which will split this into even bins along that 12.5K. This is for narrowband FM. You could tweak that if needed. -G to set the gain at 30, and you always want to make sure that you have your gain control as well as the antenna the same for any data that you have. I'm not saying that you can't change it in the future, but make sure that as you take these different scans, you are annotating it somewhere if you're going to be changing gain levels, changing antennas, because obviously you don't want to corrupt your data sets. When it comes to processing, exploiting it, and analyzing the data as part of your intelligence cycle, you don't want anything that's going to skew your results empirically. -I, integration period, I'm just saying collect it for 5 seconds each. -E, 120. I'll actually bump this up and I'll just skip through this in post. So 300 seconds, 5 minutes. And then your output file name right at the end, VHF scan. And then, you could give it a date if you wanted to, but obviously the timestamp date is in there, so you don't have to. Go ahead and enter, then you get all this stuff spit out about your scanner. I'm actually getting 2.5 megahertz instead of 2.4 from the RTL. And just open up the scan file. This will be pretty big. Get out of here. You could see this is what the data looks like. And again, like I say, this is not CSV. I mean, it's comma separated, sure, but really I call it space separated because real CSV would have header information. And the other thing that's annoying is that these DBM values that start from these values starting at column 7 over here, going all the way down to as many samples as it took. These are the actual average readings, again, across that 5-second integration time for each bin. So this number right here is, actually 150.01250 megahertz, roughly. All right, that's what it should be on that channel bandwidth, and so on and so forth. So if you try to read this with the built-in Python CSV utility, it would read all of these as their own individual columns, which would be very, very annoying. So that's why we're going to handle this as just, a regular line file. And I'll scroll all the way down to the bottom. And you see, we got 478 lines, roughly 480. And then there's a blank line at the end of it where it appends this data into. So obviously that would also give us problems because it'd be like, oh, an empty line with no data into it. So now we'll go ahead and run it. And then I'll just change the name here to VHF_scan, and then it'll start to process the data. And we also have a utility in here that'll round to the nearest 5,000, because if you have PPM error or didn't account for PPM error correction, and I haven't yet because this is, I just pulled out this brand new scanner just to make sure it worked really. There used to be comment lines inside of like old versions of RTL-power back in the day, I'm pretty sure. This is mostly made from an old script that I wrote like 4 years ago, so this is just really for safety. It just skips the comment lines. This is what's known as a list comprehension. I said I wasn't going to explain the script, but I am. So really what it's doing, it's going through all the values because we're looping it. So each line, so line 480, line 471, all these different values, we're stripping them, which means we're removing the trailing white space, which, it's like space on your keyboard. It's a hidden character, but it will mess up your code. We're splitting, and we're not providing an argument in split. That means it splits by the space. And then here, we're actually replacing the comma, and we're just replacing it with a blank. So we're stripping out the comma, not with a space, with a blank. So this is just saying remove the comma from the end of it, because otherwise it wouldn't be proper. For the date time, we're just putting the date and the time together. And then we're pulling out the megahertz low, the steps, and then we're grabbing all of the DBM values. So parts 6 with this colon that's saying after index 6, and indexes in Python start at 0. So this would be 0, 1, 2, 3, 4, 5, 6. So 6 until the end, essentially. Pull those out. And then we're going to recalculate the frequencies by using a list comprehension with a range function. And then we're going to use a zip, and essentially a zip. This isn't like zipping your files like compression. We're zipping together 2 different lists into a dictionary. So we're going to zip the frequencies because they're in the order that they come in. So we're calculating the freq off of the DBM value based on its index number, which is where this I plus I range function comes into play. Rounding the stuff off, overriding the variable essentially, and then we're just writing, a pretty easy 3-banger, date time, the frequency megahertz, and the DBM value. So the only thing you need to do, and you could put time, you don't have to in front of it, time space Python 3, that's saying run Python 3, and then give it the name of your script. You have auto completion here in VS Code, so if you start typing and hit tab, it'll just auto complete for you. And then it'll go ahead and pull that through. So it processed 123,000 data points. Here's that first entry. Here's these are the top 10 frequencies from that split by the DBM. So that doesn't mean that they're close necessarily. That just means that they're high power. It could be that you're near a federal repeater, you're near a police station, or whatnot. And then it creates all the different plots for us. It created the animation, and we are off to the races. There's a couple things in here that you could change. Obviously, you could change things like the actual names of the heat maps, the frequency bin, that's the X label, the Y label. Like, you could change these things if you want to. It doesn't really matter. It depends on what you're going to do with them, right? So we'll check out the scatter plot first. And let me pull this thing down over here. See that scatter plot nice and big. And yeah, look, the bottom 5% was about like 0.37 dBm. I think it printed it out before. I just missed what it is. So you see it's a pretty tight scatter plot with all these different sources, and you can see some things are high over here. And this is processing. Like you're in the first video, you did the collection phase of the intelligent cycle. This phase, we're doing processing and exploiting and maybe a little bit of analysis, right? So this would be something interesting to check out, right? And then obviously this stuff came out. Let me pull the terminal back up again. You know, some of these, the max frequency came out. And you remember, this is the max frequency for the entire range. So it probably scanned 152.7245 a lot of times. So this one is very high up there. So I would, plug that into cubic SDR, give it a listen or whatnot, or look it up on radio reference for your area to see what it is, or if you had like a unit in Bearcat, or if you just had like an ICOM or even a Baofeng radio, or any radio really that has an analog mode, you just plug that in and give it a listen, right? So that's what I love about SQL. Again, we process 123,000 data points. Are you going to go and pick out the top frequencies for all the data points? Probably not. So SQL does make that a little bit easier. So that's the scatter plot. Pretty simple and easy just to interpret, right? And not too different what you would see in a waterfall. The next is the heat map. And the heat map gives us a little bit of a different view. Now on the heat map, we could see, all these different dashed lines that might be indicative of like pager data, burst data. You see that here, but it could also be, other carrier waves overwhelming the RTL-SDR because it is going from a ADC, an analog to digital converter. So if you're near like a cell phone tower or something else with high power that might not be in your frequency range, you could also be attenuating it. That might appear a bit different, but you see all these like different static lines. So we are getting a lot of power readings with these stronger bars, which might just be radar as well. I'm not too far from a couple like really, really small regional air parks, and I believe they have secondary surveillance radio, so that's what it could be as well. And it might also be voice traffic. It's just really hard to tell, but the heat map gives you a bit of a different view. And then the animation. So this is a time lapse, and you could also change the animation, the frames per second, as well as the time in between all of them. And you could see this now for your entire scan. And remember, like you could set the entire range. Like you could scan from VHF low at 30 megahertz all the way up to freaking L band, or all the way up to 1.7, even though I don't know why you would do that. Well, there are reasons to do that, but there's not a lot of voice comm stuff. So let's say you're scanning from 30 to 900 or 30 to 950 or something like that. Then you could visualize this whole thing. And obviously it would be a bit different. We would do other things to like split the data frame apart by the range. And remember, that goes back to the types. So it's like, oh, hey, if the frequency starts with this, because we could convert the frequency to a float, we could segment off all of VHF. We co1 segment off UHF-1, UHF-2, UHF-3, 700, 800, 900 ISM, or even smaller bands. Like I want to take 433 out. I want to take 125 out. I want to take AIS out. I want to take ADSB out on 1090, like lower L band, things like that, right? So there's a lot more data manipulation that you could do in the processing stage. And then obviously you could also change out the SQL if you know how to write SQL, or just tune this. So it's like, oh, I want my top 20. I don't want the max. Maybe I want the average. And let's limit, let's not put the limit because we're already ordering it and descending, but just give me 15, right? So we'll just rerun this. This is easy enough to rerun, right? I mean, this is not big data by any means, but on the Pi 5, it rips through this stuff pretty quickly. So now you see we have a different look because we actually didn't take a small sample. This is just the average dBm count instead. You could also do min. You could also do max again. You cannot do that. You just give me like the actual number. It doesn't matter from when, because this is averaging across. And also this is also known as a summary aggregation. So it presents the data in a different way. But you see 18 seconds is all it'll take you to process over 100,000 results from RTL-power, get it nice and simple, data frame, proper typing support, and then you get yourself a scatter plot, you get yourself a heat map, you get yourself an animation. You could change the animation from a GIF to an MP4 if you wanted to, so you could play it back later. And just to show you, you could reset things like the interval, milliseconds between the frames. You could change the frame rate as well to like 30 frames per second. Usually you want to go with like a lower number, and then we could change this to like, 1000, and then rerun it one last time just to show you it looks different, and then I will stop talking. But that's all I really had for you today, folks. I hope that you took something away from this, and it encourages you to learn more about the Linux file system, about Python and things like that, how to write SQL. There will be more technical deep dive content to come. Trust me, I want to get you guys into machine learning, into AI, into z-scoring. I'll probably do that one next. Z-scoring is a simple anomaly detection for analytics, except you're going to need a lot of data. So make sure you're running a lot of scans, and we'll run all that data through the script here to get everything nice and prepared for you. I'll probably write something new, and let's just pull this thing up. But yeah, you see now that we lowered the frame rate and that interval, it's a bit easier to see these spikes. And then this is, if you want to pause it, obviously it's where MP4 really shines instead of just the GIF here. So this stuff is important, I think, especially to be aware of your environment for tracking emissions control, for tracking potential bad actors, for tracking just generic activity that goes on around you, whether you want to operate under or above the noise floor, inside of a frequency or not, if you want to check for sources of interference, and then eventually tracking drones and whatnot, using this as an input for radio direction finding, and all those great things that we're going to talk about in this channel. So thank you very much for listening all the way. If you did, don't forget to like, share, subscribe, comment on the video. If you want to see more of this, less of this, more of the same. And if you want to see more, obviously subscribe, hit that bell icon, select all. The most important thing, though, is yourself. Take care of yourself. If you're going through a rough time, make sure you reach out and talk to somebody, even if it's just lowly old me. Spend time with family, spend time with friends, make some new friends, maybe build yourself your own little training group and get more people into comms and signals intelligence. We're going to be doing a lot of great work in this channel together, hopefully, learning new things. And I learn from all of you all the time as well. So thank you. Eat more steaks, lift more weights, stay safe, stay well. May death find you alive. Matplotlib Hellfire.